To continue with the 1.5 day 2 notes talking about piecewise functions, we first began in class and we saw what a piecewise function is defined as. Then we looked at evaluating a piecewise function at different points and how to pick which of the different sections of a piecewise function we want depending on what x value we have. And then we started with some graphing. So the rest of this screen recording here is going to walk through some more examples. So if you feel like you got the idea from the beginning, then great, you can go ahead and try the 1.5 problems all on your own. But if you feel like you need more practice, this video is for you. So we're going to start with number 4 and then work through the rest of these examples on this page. We're going to go from 2 graphs, 2 sections of a piecewise function, up to 3. Now, piecewise functions can have as many different functions and sections as we want, but for this class, we're going to cap it at 3 just for complicated difficulty's sake. All right, so for number 4. This process is just a suggestion. When it comes to graphing, different people have different preferences for how they graph. How I will often choose to how I will show you this, I think, is a pretty organized structure that helps you work through all the pieces. If you have a way that works for you, that is great as well. So for number 4, our function is h of x is equal to -4 minus x when x is less than or equal to -3, and then -1/2 x squared when x is greater than -3. So we have these 2 sections. Thinking about shape these sections are going to take on, parent functions. This top function is a linear function, and the bottom is a quadratic. So this will help us clue in what shape we're expecting to see. And we're going to grab a section of this. So I will be grabbing on the top a section of a line, on the bottom a section of a parabola. So we'll see what this looks like. So next up, how I usually start is I will take this dividing point of our boundary, which is -3, and substitute it into my function and evaluate each function at that point. So I have a place to start with graphing. So for the top, I have -4 minus -3, which gives us -4 plus 3, or a y value of -1. So this is the point -3, -1. Then for our bottom function, we have -1/2 times -3 squared. That's -1/2 times 9, which gives us half of 9 is 4.5, so that's -4.5. Okay, so then we're going to go for the bottom function to -3, -4.5, so 1, 2, 3, 4.5, and for that dot, it will be an open circle because we do not have the equal to bar underneath. For the top function, we do have the equal to bar underneath, so we're going to go to -3, -1, and draw a closed dot. Okay, so then now, less than or equal to, or just a less than sign, in terms of x values, means we're going to go to the left direction with that top function. So to the left of this point, I want to graph -4 minus x. Well, this is a line with a slope of -1. So I want this line to be going downwards. So if from my green point, I can go over 1 to the left 1 and up 1, I can start to follow this slope and get some more points that are along this line so that I can see where this graph is going. An alternate way is we can plug in x values that are less than -3 to get output. So we could plug in -4, -5, -6. That is an alternate way. So let's go ahead and, come on, sketch this graph. There we go. Okay, so the linear ones should be pretty straightforward. When it comes to the quadratic, we just need to engage our thinking caps a little bit more. Thinking about transformations, this is a quadratic that's opening downwards because of the negative, and then it's being vertically compressed with the 1/2. There's no values shifting it to the left or the right or up or down. So this quadratic, even though it's a piecewise function, will still start at 0, 0. And since 0, 0 is to the right of -3, I can plot that point. So we're going to graph everything in this space to the right of -3 is fair game. So I'm going to try to figure out what the curve looks like that connects between the origin and here and get some accurate points. So thinking about a parabola, I could go to the left one and right one, plugging in those values. That would be -1/2 for both of my y values. And then if I went to x is -2, that's our last x value before we get to -3. Let's plug in -2. Well, that's -1/2 of 4, so that's -2. And with parabolas, it's a 2 for 1, so we can mirror it on the other side. We could even do that with that negative 4.5 point over here. And look at this. Tracing through. And then it does continue past, so let's put an arrow on the side where we don't have a closed circle at 3. This entire graph is our graph of the piecewise function for h of x here. So now this is our graph. So what you can see is this looks like a parabola that is starting at the origin going downwards. The only thing that a piecewise changes is we just cut it off at -3. We just don't draw anything past -3. All right, for our domain, I've got an arrow going to the left, to the right, and a closed circle where we have a jump. So this domain is all reals, -infinity to infinity. Looking at the range, reading from the bottom to the top, I have an arrow that's pointing downwards, covering all my negative x or all my negative y values. Traveling upwards, there is no gap in which I can draw a dot, and there's not a graph, orange or green, somewhere. So this also will have a range of -infinity to infinity. And then as a reminder, for discontinuities, we have 3 types of discontinuities. We have jump, infinite, and removable. So an infinite discontinuity is going to happen when the graph has an asymptote. We don't have that here. Removable is when the graph passes smooth through a point but just has an open circle. That does not happen at -3, so this is a jump discontinuity. And then we want to say what x value always, so at x equals -3. All right. So next up, we're going to go to number 5. We're going to do the same thing here. Think about your parent functions. Think about the shape. Okay, so for f of x equals 4 over x plus 3 when x is less than 1, and 2x minus 7 when x is greater than 1. So our boundary line here is 1. With piecewise function, these numbers are always going to be the same because we want to pick up right where we left off and not leave a gap in our x values. All right, so substituting in 1, this gives us 4 over 1 plus 3, so 4 over 4. So that is a y value of 1, so our graph goes through 1, 1. Then for our other function, we have 2 times 1 minus 7. Working that out, that gives us -5, so we go through 1, -5. You'll see, I don't know why, but -5 is really popular in this note set. We'll do a lot of points that go through -5. Okay, so moving forward, I would encourage you to then plot these points and then fill in the graph's shapes from there. So we have 1, 1 for the function on the top, and you want to ask, is it closed or open dot at that point? For the top function, less than or equal to 1, so closed dot. And then at -5, it will be our open circle because we can never have 2 closed circles. 1, 2, 3, 4, 5. Open circle. Okay, now we want to go and we want to think about what is happening with these functions. Our top function, this is a reciprocal function. This is the functions that look roughly like this. So we are going to pull some section of these curves, depending on what we see. We might only have a portion of it. We'll see what happens. And then we have 2x minus 7, which is a line. It's a linear function, linear parent function with a slope of 2. So at this point, I always think if I see a line, it's just a nice way to build confidence. Start and graph the line, and we can use the slope. So from this point, we're going to go up 2 over 1, up 2 over 1, and we can trace through these points. And we have the right side of our function. When x is greater than 1, this is our point, and I'm going to go ahead and move this dot because it doesn't look like we passed through it very well. Okay, so here comes the harder part, a reciprocal function. If you really desperately need help, you can always go to Desmos and plug in this function 4 over x plus 3, get an idea of what it looks like. The only thing is that we are only going to draw it up to where x is 1. So we are going to stop drawing it at this point 1, 1 that I currently have highlighted. We're not going to draw any of this part past it. So now we kind of have an idea of what's going to happen. Well, how did we actually get here? So going back to parent functions, they normally have asymptotes at these points. So looking at transformations, x plus 3 is going to move my asymptote, that's normally on the y-axis, right 3 units. I'm going to make this a lot skinnier. So I'm going to have an asymptote right here at x equals -3. We're also going to have an asymptote still at x or at y equals 0, following through right here. So this is my asymptote. So the next up, looking for some points. If I were to start to plug in some values, so if we wanted, we could plug in 0. If we had 0, that's 4/3, 4/3, so it's just going to be about right there. If I plugged in -1, that would give me 2, because that gives us 4/2. And then if I plugged in -3, if I plugged in -2, that would give me 4/1. So that gives us a y value of 1, 2, 3, 4. So now I can start to see where this is going. So we're going to come down from the asymptote, curve through these points, and then stop at 1. That's our cutoff. And then we can pretty much mirror and flip these. Do you see how the point closest to the asymptote went up 4 from there? We're going to do the same thing, just to the left of the asymptote. We're going to go down 1, 2, 3, 4. 1, 2, 3, 4. And you can also use the math to check this in. At this point, we were at 1, 2, 3, 4. So if we substituted in -4 for x, that would give us -4 for y. Continuing on from here, -5 gives us -2. And then these are some of our points we'll cross through. Just getting a general idea. We want to make sure that we, with reciprocal functions, make our way to hug these axes. So this is what this entire piecewise function looks like. The pink graph and the blue all together are the functions, and those highlighters there are not that's not a part of the function. It just helps us have a guiding line for where this is going to go. So technically now our function would look like this. Okay. All right, so this time for our domain, we are actually not going to have all real numbers. We have two discontinuities. We have a break right here at -3. We also have a break at 1. At 1, there is a closed circle up here, so 1 ends up getting covered, but -3, neither side from left or right hits -3. So for our domain, we need to leave out -3. So -∞ to -3, we're going to close it with a parentheses, skip over it, start back up on the other side, and go to +∞. All right, for our range, there's an arrow going down to -∞. Going here, we're covering all these y values. Even where there's a gap right here, the blue graph covers it, so nothing is left out. So this has a range of -∞ to infinity. So it does cover all y values at some point. Even if one of the graphs misses it, the other graph covers it. And then I did mention we have some discontinuities. So we have 2. At x equals -3, this line is approaching an asymptote. That is where we have an infinite discontinuity. It's heading toward positive infinity. So we have an infinite discontinuity at x equals -3. And then we have a jump discontinuity at x is equal to 1, where our piecewise gap is. Hopefully you're starting to get the hang of this. This is all extra for you. If at any point you feel like you understand it, go try it yourself on the homework. And then if you get stuck again, come back and watch it here. So we've got 2 more examples that I'm going to go through to give you some idea of how this works. And then hopefully you should be set to feel confident in doing this on your own. So for number 6, we've now got 3. We have 2 breaking points for these functions. One is at -4 and one is at 2. So let's go ahead and look. Our top function here is 3x plus 8. That again, x to the first power is linear, so this will be a straight line with a slope of 3. Now this one here, -1, there's no x on it, and that is our constant function. So this is a constant. And then this guy here is a quadratic, and this quadratic will have its vertex. It's shifted right 2, down 5, so it would have a vertex at 2, -5. So let's go ahead and start this process, and it should look pretty similar to how we've done it before, except now we have 2 points to plug in at different points. So for the top function, let's figure out at -4 where it's at. 3 times -4 plus 8, that's -12 plus +8, so that is -4. So this top function is at -4, -4, and it is equal to, so let's go ahead and put a closed circle there. The next step for our middle function, constant y value of -1. When I'm at -4, that means I'm at -1. So we're going to put an open circle on that point. And then let's jump now to 2. Same function. What happens when we're at 2? Well, guess what? It's constant. We are still at -1. And then for this graph, let's go ahead and finish off. It's going to be constant all the way through, so we can draw a horizontal line between -4 and 2. So then lastly, for our last cutoff point would be the bottom function where x is 2. So this, substituting as 2, is 2 minus 2 squared minus 5. 2 minus 2 is 0. That gives us -5. So at 2, oh, and I didn't go over far enough. Let me just finish this. We need to go over to 2. There we go. At 2, we are at -5. Hopefully I can get this. There we go. Perfect. So for our last function, 2, -5, 1, 2, 3, 4, 5, and open circle, because we can never have 2 closed circles. All right, so I can't leave it like this. This is a very sad graph. This is a very unfinished graph. So now we need to go back to the different functions. Color coding is really helpful here. So 3x plus 8. Slope of that line is +3. So to go to the left, I want to move left. So I'm going to go left 1, down 3. And it looks like now I can see I've got 2 points. I can draw a line through it. Any other points are going to be off the graph. So this is good enough for us here to sketch through this. So we've now got the left side. We've got this middle section. Lastly, we need to cover this parabola, this quadratic. 2 options depending on your comfortability level. Easiest one if you're not sure is substitute in values. Here at, go over to x equals 3. Plug in 3. And figure out what you get. If you do that, you will get -4. And then if you substitute in +4 and go from there for that, but following our pattern with how quadratics work, we go over 1, up 1, then we go over 2, and then up 4, putting us at -1. And if you do that math, I promise you it'll work. And then we could keep going from there. We would go over 3, up 9, but this is good enough to sketch through and get our half side of our parabola. So this is what our function looks like here. For the domain, again, look at the left and right. We have arrows pointing both directions. I have closed circles on my places where I have discontinuities at -4 and at 2. So this is -infinity to infinity. All right, let's check out range. Do I have an arrow pointing downwards towards the negative values? Sure do. What about upwards? Sure do. Okay, let's check the middle. Looks like in here, I have this gap. But where I have this gap, the green function is filling it in. So we cover all the y values as well. -infinity to infinity. And then lastly, piecewise functions are pretty much, except if we have a function that has its own discontinuities, they're always going to be jump discontinuities. So this will be a jump discontinuity at x equals -4 and at x equals +2. Alrighty, and last but not least, number 7. So for number 7, let's switch these bright colors here. Again, we have a cutoff at -1 and at +2. So first up, constant function at 7, flat horizontal line at y equals 7. So when I go to -1, it is less than but not equal to -1. So I'm going to go up to 7, which I believe is 1, 2, 3, 4, 5, 6, 7. Yep, right here. And then for x cubed, we have to do this twice. So I'm going to use this green here. So at -1, this is -1 cubed for the middle function, -1. That's -1 minus 1, so that's -2. So for our function at -1 and equal to it, we are at -2. So I'm going to put a closed circle. What we're going to do is we're going to fill in, get our other boundary point for the cubic, and then we'll fill it in later. So for 2 cubed minus 1 is 8 minus 1, which is 7. So at 2, we are up here at 7. And then lastly, for our purple function, we're going to plug in for 2 as well. Negative square root of 2 times 2 plus 1 on the outside. That's square root of 4, which is just regular 2. -2 plus 1, which is -1. So we are at +2, -1, open circle. So this looks like a nice, this looks very funny now. So let's go back and make sure we piece everything apart. For 7, that top function, we want to go to everything to the left of -1. It's constant at 7, so all we need to do is draw a flat horizontal line, and then it keeps going. So it keeps going to all of our negative x values. That y value will always be 7. Next up for the cubic, especially if you're uncomfortable with cubics, please substitute in values to get estimations here. So if you're not comfortable with it, let's plug some things in. Let's plug in 0. When x cubed is 0 minus 1, that gives us a y value of -1. Then let's go to +1. +1 minus 1 is 0. So what you can see here is this is where a cubic is starting to make its curve. So we've just cut off the tail end of it. So from here, cubics go up, they turn around, and then they go right up. But we're not going to go past that point. We have to stop there for this middle section. Okay, alrighty. And then lastly, for this square root function. Now, even for me right now, I'd have to do a lot of thinking about, so we're reflecting it downwards, we're stretching it twice, we're moving everything up 1 with the bottom function, negative square root of 2x plus 1. There's a lot going on. So I would start substituting in values here. If we substituted in 1, 2, 3, x equals 3, that gives me the square root of 6, which is not a great number. We could do it, but let's try to see if we can find any other nicer numbers with square roots. If I plug in 4, that's square root of 8, which is not bad. So let's see here. Let's just do that and get a decimal approximation. So if I plugged in 4, that is, where did Desmos go? There we go. Negative square root of 8 plus 1. So that gives us negative 1.83, so a little bit under -2. So when we're at -4, and we could have done the same thing with -3. So we're at -4, we're just under -2. So that would put us right about here. Thinking about nice numbers, the next multiple of 2 square root that I have is going to be plugging in 8, which is actually this last number right here. If I plugged in 8, that gives me the square root of 16, which is -4. When we're at 8, the math works out that it's going to be at a y value of 3. So then looking here as we connect this, it would look something like this and continue past from here. So we're kind of missing the like sharp curve part of this square root, but it is still moving and it's pretty wide and it's growing out from here. So this is what this graph looks like. Definitely probably our funkiest of all of them so far. So let's go ahead now and answer our 3 questions: domain, range, and discontinuities. So for the domain, again, because we've got equal to lines at all these breakpoints, it is still negative infinity to infinity. The only time it wasn't was when one of the actual functions itself had its own discontinuity. For the range, for this one, let's be very careful here. Do I have an arrow pointing downwards? We do. With square roots, it levels off, but it does keep growing. So this arrow is going to keep reaching negative y values as it goes. So it will come from negative infinity. Now let's keep going. So I cover all these negative y values with the purple function. Then it kind of switches and the green covers all these here. And then we hit 7. And at 7, we have this flat line, but no other value greater than 7 gets covered. So it's going to stop at 7, and it's done at 7. So that is it. This is our function. And then we have 2 jump discontinuities. We have a jump discontinuity at x is equal to -1 and at x is equal to 2. So this has a lot of work. It has a lot of notation. Please make sure that you are being precise. You are constantly plugging in points so we are getting accurate values as we work this through. Hope this is helpful. Go ahead and jump over to that 1.5 day 2 homework in the 1.5 packet and complete the problems. Try this on your own and then let me know as you have questions.